you. Thank you, everyone, for being interested in our project. And I just want to acknowledge Heather Crowley on the line, the Alaska Boehm region. It was a real pleasure to work with Heather and to be the contractor selected to do this work. My background is primarily oil spill preparedness and response, which has also elements in planning and exercises and also scientific studies, how you bring science to help people make better decisions. And my role in the past has been to advise decision makers on kind of what the best thing to do is about oil spills and dispersants, one of the controversial tools. And one of the first pieces of information that's important in any oil spill is how they weather. And I did respond to the Exxon Valdez, and I was on scene for Deepwater Horizon as well. And one of the other interesting ones that I responded to was in Bolivia, in the Altiplano, where you really didn't have any tidal waters at all. And you just learn so much on every incident. So another piece of that, I think my background is also a real interest in not just how decision makers use information to form their opinions about what should be done and choices, but also communities who are affected by oil spills. So during the Exxon Valdez, I was assigned to work with subsistence fishermen about their seafood sampling, testing, interpretation, and of what the oil would do if they consumed it over time, and wound up with subsistence and fishermen people over the years. I find it to be a very complicated issue and one that crosses over a lot of different agencies and expertise, and so it's not one that is owned very well by a single agency, and so it just seems complicated to solve. But that's a little bit about my background, I guess, and shall I just go ahead and launch on into the slides?
Please,
if anybody has, yep, and if you have any questions, please feel free to ask them. This project, I really am a believer in understand the weathering of oil if you're trying to respond to a spill. And I've worked with SINTEF, which is a nonprofit scientific organization in Norway that's looked at oil spills for a very long time, worked with them. And so together we bid on this scope of work and RFP, and we won it. But truth be told, the majority of the work was theirs, and we were really sort of the user interface and the contract interface in the United States. And so I'll tell you a little bit about the work, the project, as well as the work that we did. And then when Guillermo contacted me, said you all were very interested in kind of how this could be applied real world and interested in dispersants too. So we'll end with that. Our project objectives were to obtain weathering characteristics of, it was determined, 6 different oils that are representative of the Alaska Outer Continental Shelf. And in this way, we wound up doing kind of 3 crude oils and 3 refined products that are transported in the offshore waters in Alaska. This information is to expand the libraries of existing oil weathering models. The SINTEF one is the OWM, the oil weathering model, as well as NOAA's automated data inquiry for oil spills, which is really most of the time known as ADIOS. So the real purpose of this was to do these studies to be able to import the data into the both weathering models, so the predictions about how these oils would behave could be made going forward. Okay, you're probably aware more than I am that the Alaska OCS region uses SINTEF's oil weathering model tool to provide quantitative set of spill weathering parameters for use in NEPA assessments. Looks like there's a funny little covering up the graphic for some reason. Anyway, this information about oil weathering is used to make estimates regarding mass balance of oil spills through time. So for example, an important thing is when a spill happens, how much evaporates very quickly versus how much is likely to remain. And if anybody followed the Deepwater Horizon incident in terms of its mass budget, the oil emulsifies when it picks up water, and so in some cases you can wind up having more volume that's collected than originally spilled, but all these things go into the mass balance in trying to address what to do about the spill and how the oil is behaving. So this information is really important for oil spill preparedness, to see if you've got the right kind of equipment and enough equipment and techniques and strategies available to combat a spill should one occur in spite of everyone's best efforts to prevent it. The information is used not only by BOEM but also its sister agency, BSEE. We had a number of tasks. The only ones I'm going to talk about today are really 3 through 5, a little bit about the bench scale testing that was done, the mesoscale testing, and then the fact that how the results were provided to the developers using the weathering models. Task 6 was to prepare the final report, which has already been delivered. I think we delivered it the end of September. So it should be, I'm not sure, I think it's on the, I don't know, Heather, are you there? Is it on the website somewhere? I haven't actually checked.
She doesn't have audio, I think.
Audio, okay.
Yeah.
Oh, she's typing. I see she's typing, though. She can say whether it's online if you wanted to read it. So the first thing we had to do was obtain about 25 to 80 liters of each of the oils once they were identified, and that was not a trivial thing to do, to have them obtained. Yep, it's been posted on the ESPIS system. Thanks, Heather. And so to obtain the oil and ship it to Norway, so there were 3 crude oils which were obtained. Alpine from ConocoPhillips. See, I'm not sure I've actually said this out loud. Do you all say Kuparuk? Is that how you would pronounce it? Kuparuk crude oil from ConocoPhillips also, and North Star oil from Hilcorp. Thanks, Heather. Okay, thank you all. And then we had also 3 refined oils because they are used on in the Arctic waters. So we had an automotive diesel oil, ADO, marine diesel oil, MGO, and a wide range gas oil, WRG. And because those are refined and very similar to products which are used in Europe, they were actually obtained from a refinery in Norway, not too far from Sintef. So the location of these oils, you can see, here's the Alpine, the North Star, and the Kuparuk oils. And let's see, let's go on. So the laboratory tests, which are bed scale, were conducted to obtain more information about the chemical composition of the oils and their physical properties. Gas chromatographic characterization was done. They specifically wanted to learn more about the asphaltene and wax content and the physical properties of the fresh and weathered residues. And again, for oil spills and to see how oil behaves if it is released into the environment, emulsifying properties are really important. So studies were done to see to what extent water would be readily taken up and to form an emulsion, as well as to look at would an emulsion breaker be effective, efficient at breaking those emulsions, or if they were stable, and also the viscosity of the water-free residues and emulsified residues. And the bench scale testing of these crude oils, the alpine oils, I think that some of the key parameters that are of interest to me, it's a light paraffinic crude oil that corresponds to an API gravity of 38.4. The Exxon Valdez, for example, oil was, API gravity was 29. Deepwater Horizon, Macondo's oil was 35.2. So API gravity, the lower the number, the heavier the oil. So Alaska North Slope, as you all probably know, is a heavy crude. These oils that were done for this testing, as well as Deepwater Horizon, are considered medium crudes. So this talks a little bit about the actual content, and it's funny again, it's got something over the, but basically it did form a stable emulsion when weathered. The Kuparuk was let's see, it was a little heavier than the Alpine oil, it did form highly stable and viscous emulsions. And the North Star was much lighter than the other two, API gravity of 50, and was regarded as low emulsifying crude oil that formed loose and unstable emulsions with low viscosities. The bench scale testing of refined products is summarized on this slide. Key points is that they actually, for being refined products, they had about the same API gravity in the range of a medium crude oil. All three of them were in that range. You can see the automotive diesel oil weathered residue did not emulsify during the bench scale testing and didn't show any water uptake. The marine gas oil also did not show emulsification or water uptake. And the wide-range gas oil did show some emulsifying properties, but they were very unstable and easily broke up after standing less than an hour. Let's see, go down here. In terms of how these categorize, Syntef has done quite a bit of weathering of oils, especially in Norway, but also they've done some in the United States. So you can see that our three oils here compare, two of them are more paraffinic, the other one is more alsifenic, and you can see the other in the blue circles where they are relative to other Syntef oils from the same region that they've looked at before. Now the Flume basin test is a mesoscale test, and in the Syntef laboratory they have a flume that they've built, and they do a lot of these tests. These are done at 10 degrees C, and the ones that are really important for spills at sea are the percent that's evaporated, how the oil, what percent stays on the water surface, and what, if any, disperses into the water column, either naturally or with the addition of chemicals. Photographs were taken of each oil, and they were about the same time frames, but not perfectly uniform. So you can see the idea was to look at their visual appearance at various time steps, typically 30 minutes after being put into the flume, an hour, 2, 3, 4, 12, 24, 48, and 72 hours. But you can see there's exceptions. MGO and WRG were only at 48 hours because there was only, after that time, there wasn't much oil left on the surface. Then dispersants were applied after they'd been on the water surface after 72 hours. And just a note, this is probably realistic for many places that it might take 72 hours to possibly to mount some application, but I think in the United States anyway, our regulations require that companies have to have the capability to apply surface usage dispersants if they're approved within about 7 hours. So our reality in the United States in regulation compared to this test is a little different. Okay, next slide. You can see the appearance, and we decided in the interest of time just to give you an example, not to go through each one, but the alpine crude oil, you can see how it changes color after 1 hour, after 72 hours, and then an hour after the first application of dispersants, and 2 hours after the second application of dispersants. And please pay attention to this range of colors here, because that will be kind of important to the latter part of the presentation that I'll give. It's really interesting to see how the oil changes color over time when it picks up water. Okay, so the dispersant application, they all, I think, some of them were not necessary to apply dispersants. It didn't really contribute very much. For the alpine oil, minor surface oil was observed after it was applied. And the ratios here were important. The alpine is dispersant to oil ratio of 1 to 33. In the real world, they typically do like 1 to 20. But anyway, it was a significant potential for dispersant use as a response option demonstrated by this test in the Flume. Kuparic, 68% of the total volume oil was available for dispersion, and there was some artificial turbulence applied to the slick after dispersant application, as you might find in a real spill situation, to increase the efficiency of dispersant use in this oil. I don't know how many people on the call are accustomed to use of dispersants, but a general rule of thumb is that, up until Deepwater Horizon anyway, is that surface applications of dispersants do best when there is some mixing energy provided by the wave heights, 2 to 3 feet or more of wave height really helps boost the efficiency of the dispersants. During Deepwater Horizon, we had periods of very flat, calm waters where we had less than a foot of sea state, of wave height. And we did do a test during that spill and found that for that particular kind of oil in that situation with the air temperatures and the way the oil was after really more of a weathered state, that dispersants were still effective on that oil even with no wave energy. But in the Flume, they typically tried to create conditions that would result in dispersion to see exactly how well dispersants would work. Corexit 9500, I don't think I mentioned, was the dispersant that was used in these mesoscale tests, and that was the same dispersant that was used the most in Deepwater Horizon. It wasn't the only one, but it was the one that was used probably 80% of the time. So the North Star oil also was dispersed into the water column pretty easily. The ADO was also dispersed pretty easily, but the latter two didn't really need to have any dispersant application because they broke up and dispersed naturally pretty readily. Now, in terms of the data that we found that would go into the oil weathering models, the results from Task 3 and Task 4 were summarized into the technical reports that there was a certain kind of format spreadsheet of data that was necessary to deliver to both NOAA and provide to SINTEF, a different part of SINTEF, to put into their oil weathering model. And at this point, I think actually inputting it into the weathering model was not part of that project. This project, that's a separate activity. So our conclusions from this is that the weathering of spilled oil and the persistence of the components of the oil varies depending upon the specific characteristics of the oil, and that's something that's consistent with what was the previous understanding. The bench scale weathering studies yielded consistent data for input into the weathering models. That was really important, that it be consistent with the methodologies and the kind of results that we're seeing previously. The mesoscale testing was supplemental to the bench scale testing and was conducted to provide the information related to potential field operations, and especially the visual assessments of effectiveness after adding Corexit 9500 to oils that had weathered for about 72 hours. So the last part of the talk I thought I would share with you are some related activities that are beyond the project scope, effectiveness testing and determining the specific time window, which is what the Norwegians say, or the window of opportunity that we say, for dispersant use is something that we didn't really try to nail that down. Rather, we followed standard procedures rather than trying to say, okay, well, what's the longest that you could apply dispersants before they're no longer effective, the oil is too weathered. So we didn't do that part in here. And we didn't take the data that was put into the oil weathering models and actually then model the weathering to assess the output prediction, which you can use for predictions of the weathering properties. So that's something that certainly can be done now that the data's been input into the models. And the other thing that I added, I guess, for interest, that it's a particular interest of mine, having been a responder, and that those of you working in the Arctic may find interesting too, is it'd be ideal at some point to incorporate weathering data into a responder guide for surface applications of dispersants, especially in case of any kind of situation of a blowout, or potentially for even boat spray applications of dispersants. And when I think about the Arctic, and I talk to the guys in Norway, they have a smaller coast. They use dispersants in a much more tactical way than we do with our big coast and potential large-scale spills. We tend to use fixed-wing aircraft, which is a much larger brush and a much different situation. But in Norway, they use them, to kind of prevent a certain slick that reaches a sensitive area, which might be the kind of application that would be more appropriate for an Arctic situation. So let me just show you a little bit what I mean. So during Deepwater Horizon, we had so many questions about why is the oil red? It doesn't look like regular oil. And so with Syntef's previous work, they were able to deliver this mosaic of oil weathering properties that was able to answer people's questions about how the oil visual colors change with the addition of wind speed and over time. And so, you can kind of look at the different visual characteristics of the oil as it changes. And of course, that's in Norwegian summer conditions. But this is really pretty applicable to the situation we had in Deepwater Horizon. Fresh oil, is pretty black, and the only place in a blowout you have that is pretty close to where it might rise to the surface. In shallow waters, you probably have much more dark oil. In deeper waters, you could still have deep, oil, but it would lose a lot of the light ends as it comes to the surface. So this is an example from Deepwater Horizon where the oils came to the surface. This is without treatment at the subsea with dispersants, but the oil would come to the surface, and you can see this is a boat spray application right here. These little nozzles that are coming down, and the creamy color is a visual confirmation of effectiveness. This kind of what they call cafe au lait, and that was traditionally one of the most effective ways to assess whether or not dispersants are effective in removing the oil from the surface. Now, in Deepwater Horizon, however, this is what the oil looked like, because as the spill continued, they sort of divided up the area into, they partitioned the actual geographic area into workspaces for different types of equipment. So the idea was within about the 5 miles or 5 kilometers around the source, they called that simultaneous operations. They had a lot of heavy equipment that was being used to try and cap the oil. And so that was a very busy area, and a lot, the actual spill control measures, I shouldn't say spill control, but oil treatment measures or ways to capture the oil were limited inside that area. So by the time the oil got outside that 5-mile area, it had already weathered a little bit. And because in this country, and maybe in many other countries too, the first preferred technique is mechanical recovery. And so the mechanical recovery options were given the first bit of oil, basically, the freshest oil to try to capture before it had a chance to spread any further. The next technique that was given, the freshest oil, you could say, was in situ burning. And therefore, in that spill, aerial dispersants were given the oil once it moved away from those two areas where mechanical and that escaped, basically, mechanical and in situ burning. So in a blowout situation, it's possible that aerial dispersants might be applied to oil that's weathered and not fresh oil, different than a ship spill. So what we found in Deepwater Horizon is that the idea of effectiveness, that cafe au lait that you saw, was really not a good metric to assess whether or not spills, the use of dispersants on that spill was effective. And of course, if something's not effective, you don't want to use it. So it's kind of important for a blowout situation to think carefully about what is our definition of dispersant effectiveness. It's probably not going to be 100%. You might say, well, if it reduces the oil on the surface by 50%, that's still better than leaving the oil on the surface if we can't capture it by mechanical means. And in the Arctic, of course, if you have an ice situation, in situ burning is definitely, I think, a preferred technique in terms of effectively encountering the oil and trying to limit the potential side effects of logistics, of lots and lots of boats and waste disposal and that kind of thing. So in my perfect world, I guess, I would encourage agencies to obtain more information about the weathering of oils that are transported or produced in a particular area, and to try and get a visual scale of how the color relates to weathering, degree of weathering, and how that relates to the degree of emulsification, which in turn would equate to, is it even worth applying dispersants? And so I've gone ahead and put here for you to have an example of what I mean. I worked on aerial dispersants during Deepwater Horizon, and so I was trying to help responders know, is that a slick we should try and disperse or not? And so we were trying to come up with this information during the incident, which was a very difficult thing to do because people have different ways of describing oil, of seeing it, where is it, what does it mean? And the color really had nothing to equate to viscosity or the degree of weathering. And if we really want to be prepared, this is the kind of information that I think is going to be most helpful to a prolonged event where we might have to consider the use of surface applications of dispersants. So I think that probably concludes the overview of the project and the way that I think this information can be applied in a real world situation. And I guess I'd like to just underscore again how important I think this project was. And I think through the example I've shown you, it's very directly relevant to the kind of work that would need to be done in the event of a blowout situation. So I'm happy to take any questions you might have.
Thank you, Anne. We have time for one or two questions for Anne.
Yep.
And I'll just remind everybody that you can also type your question into the chat box if you don't have audio. And remember to unmute yourself if you're on mute.
Right. So I see Ian Hartwell asked a question, and absolutely right. Part of the issue was that it had already weathered by the time it rose to the surface. So absolutely, even that Cafe Au Lait picture I showed you was still, I guess, the freshest it was going to be on the surface. And then the other pictures I showed were that it had weathered even more than that.
Shen, do you have a question?
Yes, I just wonder how effective the dispersant is on the non-weathered oil versus weathered oil. Do you have some comparison on that?
I'm sorry, what was a weathered oil?
Yeah, I just, you said that dispersion, like you discussed this dispersion on these weathered oil, but how effective it is on these different effectiveness of dispersion on weathered oil versus non-weathered oil? Well,
so here's an example of this was surface Deepwater Horizon oil, which means it did come up to the surface, and as Ian pointed out, it had already weathered, but you could see that it was still able to be dispersed. And in terms of numbers of percent effectiveness, I don't believe that in the response community we've come up with real numbers to indicate, to equate what a visual portrayal of effectiveness is, how that equates to a numerical metric. And I think it would be great to do that. So this was definitely an effective application of dispersants. And then this was before aerial dispersants were applied. So this is clearly a weathered oil. And this is what happened after the aerial dispersants were applied. So it was effective in reducing the surface slick, and you could probably do some sort of, somebody who's really good with volumes or, areas could say, well, maybe it was, I don't know, 60% effective of removing that weathered oil.
Hey, this is Heather. I thought I would dial in so I could actually speak. I also wanted to just point out that going back to the original study and the study results, in your report you did include a lot of really nice photographs from the Flume, including what happened with some of the different oils after the dispersant were applied, and of course those oils were all weathered by the time the dispersants had been applied, and so some of them, there's some really striking photos within the report, and so that is one thing that can help answer Jen's question.
Yep, thank you, Heather, and I'm glad it's up there already on the website.
Yes, it's at bohm.gov/ESPIS. You can search for it.
Thank you both. We need to move on with